Hi, everybody. Thank you for joining us for the glTF webinar. My name is Kathleen Matson. I do marketing for Khronos, and I just want to go over a few notes before we get started. First, we are making a video of this, so you don't have to take a zillion notes. You can just review the video, and you will receive an email in a couple of hours telling you where you can go to download that. Next, we are very interested in any questions you might have, and we have set aside space at the end of this webinar to answer your questions. What you can do during the webinar, if you find that you have a question, look for the question mark icon on your GoToWebinar panel. Click that, type your question, and then at the end of the webinar, we will read and answer all of those questions. All right. Well, that's it. I'm going to turn you over now to Marco Hutter, and he will do the presentation. Thanks. It's all yours, Marco.
So, thanks for the introduction, and welcome to the glTF webinar. We'll start with a short introduction about what glTF is and what it is developed for. So first of all, glTF is the GL transmission format. It's an open standard developed by Khronos, and it's designed for the efficient transfer of 3D assets over the web, mainly over the web. This imposes several requirements for the format. It should be versatile to represent different kinds of 3D assets. It should be compact for an easy and efficient transmission, and it should be easy to process it on client side. In this image, you can see that it's sometimes referred to as a JPEG for 3D data. The idea is to develop a format that is universally accepted by a broad variance of clients, so that you have one format that you can distribute, and you can be sure that every client has the capability to view and read this 3D asset. A short outline of the contents of this presentation. It's roughly based on a tutorial series that will be published under the link that you see on the slide. The rough structure of this tutorial is to explain the concepts that can be represented with a glTF asset, and it's a step-by-step tutorial. So it's really showing each feature of glTF with a small, simple, actual glTF asset. So there are examples for simple geometry, animations, materials, textures, and vertex skinning. And you can have a look at each of these functionalities or features of glTF in these simple examples. This tutorial is targeting glTF 2.0. That's really cutting edge. It's just being finalized. You can see a link to the pull request for the glTF 2 specification here. And in order to make clear what the purpose of glTF is, let's have a look at the content pipeline as it is now or today. There are several different data sources, and for example, there may be laser scanners or other forms of 3D scanners that produce geometry data, usually raw geometry data consisting of possibly millions of vertices and edges and faces. And there are different authoring applications that produce more sophisticated 3D scenes with additional features, for example, animations or lights, cameras, and sophisticated materials. And all these different data sources store their 3D assets in different file formats. For example, for raw 3D data, there are OBJ files or STL files, and the authoring applications also have their dedicated file formats, Blender, Maya, and 3ds Max, for example. And on the bottom, you can see different runtime applications that are supposed to show 3D assets, 3D data, and these applications are built on different graphics APIs. There's, on the one hand, the family of GL APIs, OpenGL, WebGL, and OpenGL ES, but also Vulkan or DirectX. And now the big question mark is, how are these 3D assets brought to the applications? There's one solution that is currently used and that has several drawbacks. The common strategy is now to create importers and converters. So every application selects a set of file formats that it wants to support and has to write an importer or a converter for an existing file format to be able to read and display the 3D asset. And of course, this does not really scale well. We cannot write converters between all pairs of possible file formats. And additionally, most of these file formats are not intended to be pure delivery formats for 3D applications. And now we see how it could look like with glTF. There's a different set of converters for file formats to glTF. And for example, for the authoring applications, there's already a common file format, Collada. And this can also be converted to glTF. And glTF is the format that is intended for the last mile, for really delivering a 3D asset to a client, to an application that is supposed to only show this 3D asset. It's not a general exchange format. For this purpose, there are things like Collada. That's really an exchange format for different authoring applications where Collada tries to retain as much of the scene and structure information of a 3D asset as possible, whereas glTF is really intended to deliver to the client what is necessary to display the 3D asset. So this comes together with several goals during the development of glTF. As already mentioned before, it should be versatile, compact, and easy to parse. And on this slide, you can see an example. For example, this plane geometry, this heavy Yoda example. As an OBJ file, it requires 90 megabytes, and that's really a lot. You can hardly transfer this over the web in real time. So the reason for that is that OBJ is not intended as a delivery format. It's a compact representation, but it still stores the geometry data as plain text, and it has to be parsed on client side and converted into the form of 3D data that can actually be used for rendering. In contrast to that, the same asset as a glTF asset consists of only 19 megabytes. Similarly, you can describe complex scenes with glTF. On the right-hand side, you can see an example that is as a Collada file, it has 5.3 megabytes, and as a glTF asset, it's less than half of that. So glTF is capable of representing plane geometry in a very compact form, as well as complex scenes with animations and materials and really complex 3D assets. And in both cases, the assets can easily be consumed by clients. So the core of glTF is a JSON file that basically describes the scene structure and the entities that appear in the asset. And the geometry data, the actual geometry data and vertex attributes, is stored in binary form. So there's no decoding necessarily on client side. The client can just read the data and use it for rendering as it is. So here's an example of the adaptation, the level of adaptation of glTF that already exists. There are already different libraries, several different libraries that support glTF as one of their input formats. For example, 3JS, that's very common, Babylon.js, Grimoire GL, Cesium, CuGL, and GLBoost, and all these already natively support glTF as one delivery format for their assets. There's also a link to a comparison of different loaders and viewers, where you can see how well each of these libraries supports the different glTF features. Additionally, glTF has reached a broad support or acceptance in the industry. There are already different applications that employ glTF as one of their presentation formats or as their main presentation format. And it really has a large scope of different possible application cases. For example, you can imagine that it's used for product configurations or product presentation, or as a format for general 3D asset libraries, for example, for cultural heritage digitization, or you can imagine a museum or an exhibition of scanned cultural heritage artifacts that are displayed and they can view online in the browser. It can also be used as a basis for example, architecture planning, where you can combine different elements of housing or furniture and interior design to plan the layout of houses or flats. It's also used in geoinformation system, that's cesium, where you can use the 3D assets as a basis for city planning and general geoinformation systems. And Biodigital is using glTF as a presentation format for educational purposes in the area of medical education and health education. And additionally, there's a large list of supporters who have announced support of glTF. So you can see that glTF really has a great impact on the industry, and it's on its best way to become a format that is generally accepted by different clients and supported by different applications. Recently, we've seen that there's a WordPress plugin for glTF, so it's hopefully it will soon be really as broadly accepted as JPEG, for example. Coming to the technical part, the basic idea of glTF, or the basic file structure of a glTF asset, is that the core is represented as a JSON file. That's the main glTF file. And it contains the information about the scene structure and entities that appear in this scene. For example, cameras, animations, possibly lights sooner or later. And these elements, these entities, refer to, for example, geometry data or image data, and these are represented as links to external files. So the binary geometry data is stored in binary files, and the images are usually stored as JPEG or PNG files because they are already compressed and really compact and easy to decode on client side. Additionally, external resources can be embedded into the JSON as data URIs. Then it's called an embedded glTF file. This has the advantage that you only have one JSON file that you have to transfer without any external references. Comes at the cost of a slightly larger file size, but maybe advantages in some situations. Basic structure of the JSON part is really simple. It consists of several entities that are shown on this slide. You can see basic scene structure consisting of nodes, and these nodes form a scene hierarchy. We come to that in a few minutes. And meshes and cameras are attached to these nodes. I will not go through all these elements right now, but they will later be explained in detail. You can see on this slide that there are really few basic elements that are used for assembling possibly complex scenes, as well as simple plain files with geometry in them. Here's an example of a glTF asset. This is supposed to be the minimal glTF asset that can exist at all. It's a simple triangle, so you can see that there's a complete valid glTF asset on a single slide. You can actually copy and paste this into a viewer, and it should be able to display it. It's glTF version 2.0. There are not yet many viewers, but we hope that there will be broader support really soon. Coming back to the contents of the actual JSON part, I already mentioned that there's a basic scene structure described via nodes, and these nodes define a hierarchy. You can imagine it like a small sort of scene graph. It's really a basic scene structure, and each of these nodes can have a local transform that can either be given as a matrix or as translation, rotation, and scale. So you can concatenate different nodes to achieve, for example, moving groups of geometry data, or you can also attach cameras to these nodes, and with the local transforms of the nodes you can represent camera flights, for example. This is the basic scene structure, and now the elements that are attached to the nodes. There are, for example, the cameras. Different forms of cameras are supported here. You can see an example of a perspective camera and an orthographic camera. They are both attached to nodes and are observing a mesh that is attached to another node. You can see the resulting rendering of this box in the lower part, where the perspective camera has a view frustum that causes a perspective distortion, and the orthographic camera does simply an orthographic projection. The actual geometry data is stored in buffers, in the binary buffers that I already mentioned at the beginning. These buffers are stored in external files in binary form, so they can directly be loaded by the client. And this raw data for itself does not have an inherent structure or meaning. It's just raw binary data, and the interpretation of this raw binary data is accomplished on client side by using buffer views and accessors. A buffer view just defines a part of a buffer, just cuts out a slice of the buffer, and the accessor defines the data type and layout of the data that is contained in the buffer view. For example, whether it's 3D vectors of floating point values or indices as integer values, for example. And the advantage here is that you can take the data from a buffer view and send it to the graphics card, and the result will appear on the screen. It's directly in the format that will be used, for example, in the calls to GL Vertex attribute pointer. So you don't have to decode or parse or interpret the data in any way. You just read it as it is and can send it directly to the graphics card, which is very important for the client in order to efficiently display the 3D assets. And another example of the elements that may appear in the scene is animations. An animation basically reads data from an accessor. In this example, you can see an accessor for the times, which are keyframe times, and an accessor for the rotations. These are quaternions describing the rotation of an object at the respective keyframe times. So the example shows a rotating triangle that consists of a simple mesh attached to a node, and the animation reads the input data from the accessors and forwards this information, interpolated accordingly, to the rotation property of a node. The result will, in this example, be a rotating triangle. You can imagine that you can forward animation information to the to different properties of a node and therefore model more complex animations. But this is just intended as a basic example showing the concept of an animation, reading from accessors and forwarding the keyframe, the interpolated keyframe values to the rotation property of a node. The actual representation of the geometry data in a glTF asset is also based on accessors. In this case, this example shows a simple mesh. Each mesh consists of a set of mesh primitives, and these mesh primitives assemble the set of accessors that provide the vertex attributes. For example, here is shown a triangle that has two attributes: position and normal and texture coordinates attributes. And these accessor data then are accessed via indices. So, for example, you can have an indexed mesh or a mesh without indices, and each of these accessors provides the data for one attribute. And again, this is the data in a form that can directly be sent to OpenGL or to any other graphics API, because it's just the raw data consisting of floating point values already in a format suitable for being sent to the underlying graphics API. So again, there's no decoding involved, just can be sent to the rendering engine in this case. More complex topic now, materials. Each mesh primitive can refer to the material which shows the material that the respective mesh primitive should be rendered with. The material itself only stores a basic set of parameters, and there are different possible parameter sets. In the example, you see some spheres that are rendered with different parameters. And these parameters in this example are the metallicness and the roughness. This is based on a physically based material description. And this physically based rendering will be part of glTF 2.0. And the interesting thing is that this is the first time that physically based rendering is on a way of being standardized in a coordinated effort. There's really the first time that a group of experts came together in order to standardize the representation, the underlying representation for physically based rendering. There are different possible workflows for representing the physical properties of material for rendering, and glTF now defines one standard representation that is supposed to be supported by a broad range of clients. So you can have one asset and transfer it to different clients, and with this very compact material representation you can achieve the same rendered result for all the clients. I think this is really the first time that such a standardization effort for physically based rendering has been undertaken. For legacy, or yeah, you shouldn't call it legacy, but for existing OpenGL-based or WebGL-based implementations of renderers, there's also a concept of techniques. This is for glTF 2.0. This will be an extension. It's specifically designed for rendering using the GL family of APIs, WebGL, OpenGL, or OpenGL-ES. In this case, materials are represented with techniques. The techniques are a description of a general description of materials. So the fast forward that is summarized on this slide is that a material can be considered as an instance of a technique. The technique refers to a program, which is basically a standard OpenGL program. And the program refers to GLSL shaders. And I have an example showing what the technique actually comprises. The technique contains a set of parameters, and these parameters correspond to the attributes and uniforms of a GLSL shader program. So each technique contains a description of the inputs for the GLSL program, containing information about the data type, the data layout. For example, in this example, you can see the positions which are 3D vectors, the colors which are 4D vectors, or the light direction, which is a single 3D vector. And a description of these parameters is given in the technique. So the technique is a description of these parameters that can be read programmatically. You can look up the technique information in the JSON file, and then you know how to set the inputs for your shader program. A short side note: the shaders, the actual GLSL shaders, are stored in external files, similarly to the binary data and image data. So these external GLSL shaders can be read into strings and directly be compiled with OpenGL. The concept of materials and techniques is, as I mentioned before, that materials are instances of techniques. So one technique defines a set of parameters, and each material is then an instance of this technique where several parameter values are fixed. I've added an example here. You can have the same technique and one material where the parameter values are the sphere positions, a color that represents an RGBA color, a red color, and a certain light direction. And when using this material for a mesh primitive, for rendering a mesh primitive, then the result will be a red sphere. Similarly, you can have a material that is an instance of the same technique, but the input values for the positions are now the positions of a box, a different color, blue in this case, and a different light direction. And you can see that using the same technique and instantiating different materials with that, you can render completely different objects using the same shader programs and the same GLSL implementations. Another element that may be contained in the JSON via a reference to an external image file is the texture. A texture is basically the input for a sampler 2D uniform variable in the context of technique-based rendering, of GLSL-based rendering. And each technique refers to an image. The images are stored in external files and can be read, and then the image is used as one input for the technique. So the technique parameter says that the input type required there is a texture, a sampler 2D input, and one can instantiate a material and assign a certain image as this input. And on the right-hand side, you will see the resulting rendering, a textured square in this example. A somewhat more complex topic is the skins, vertex skinning. This is the point where multiple elements of a glTF asset come together. I tried to summarize the basic idea of vertex skinning on this slide. The basic idea is to have a skeleton consisting of joints, and the implicit connections between these joints are considered as the nodes of the skeleton. So you can define a skeleton hierarchy using the same nodes or the same concept of nodes that is also used for structuring the scene. And this skeleton is then combined with a mesh, with the vertex positions of a mesh, basically, to obtain something that is called a skinned mesh, where you can imagine that the vertices are attached to the skeleton based on certain rules. And the result is that when you apply transformations to the joint nodes, then the skeleton will deform and the vertices will be moved accordingly. So this is, for example, used for character animation or for more sophisticated deformations that are not just rigid body transformations. Try to explain the elements that are required for vertex skinning here in a little more detail. In order to define the rules that are used for deforming the vertices based on the skeleton pose, each vertex needs information about which joints affect this vertex and how strongly these joints will affect the vertex. And this is accomplished with also with accessor data, namely with joints and weights information. So on the left-hand side, you can see that the weights, how strongly each joint should affect the vertex, are low for joint 0 for the upper vertex and high for joint 0 for the lower vertex. And on the right-hand side, you can see that the influence that joint 1 has for the upper vertex is high, and the influence that joint 1 has for the lower vertex is low. And the effect will be that when you apply a transformation to the skeleton bones, or to the nodes that are the joints between the skeleton bones, then the mesh geometry will move accordingly together with the skeleton. In the upper right hand, you can see an example. This is also one of the examples that is used in the tutorial for explaining all this in more detail. But the basic idea is that you can describe more complex character animations in a glTF asset using vertex skinning. Here's a general overview of different resources for glTF. The main resource is basically the landing page by Khronos and the GitHub repository, where you can find all the most important links. There's also a repository containing the sample models. There are several simple models for learning the basic concepts, and they will also include the sample models that are used in the tutorial, where you can examine each concept and have a minimal example basically for each concept. But there are also more complex models, real-world examples for testing, for example, your loaders or viewers. There's an asset validator that is online on GitHub, and there's also a tool, an online tool where you can simply drag and drop your assets to make sure that they comply to the specification. Additionally, there are several converters for existing file formats to convert them to glTF. Most importantly, maybe Collada for converting when you have an authoring application that like Blender or 3ds Max, then you can always export Collada files, and with Collada to glTF you can convert these Collada files into glTF assets. There's also a converter for OBJ files, because that's a very common export format for plain geometry data, and you can also just drag and drop an OBJ file into an online converter and convert it to glTF. This is, the link for this online converter is also mentioned there. It's provided by Cesium. This also includes a viewer, so you can directly drag and drop your Collada files, for example, and see a preview of the resulting glTF asset, and also download the resulting glTF asset. When you want to get started with glTF, there's some some possible roadmap by here sorted by increasing complexity or difficulty. The basic overview can be acquired by I've created an overview image roughly in the style of the Khronos reference pages, where you can see the connections between the entities that may appear in a glTF asset and what each entity consists of and how it's connected to other entities. It's really intended as a rough overview. Then you can explore each of these concepts based on the sample model. So when you're, for example, particularly interested in vertex skinning, then you can have a look at the skinning examples that are shown in the sample models repository. And the details of these concepts will then be explained in the tutorial, where you can that are based on the basic example models. And when you really want to know the details, then you can look them up in the specification, where the actual JSON format is specified and all the valid parameter values and all that. When you intend to write a glTF loader or viewer, then I try to summarize the concepts of glTF here, roughly sorted from simple to somewhat harder on the right-hand side. The basic scene hierarchy traversal, just consisting of the scenes and nodes, is rather simple. You can just usually recursively traverse the scenes and nodes in the node hierarchy, and the next step would be to process the elements, the simple elements that are attached to the nodes, for example, the cameras and animations. And later you may try to tackle the compound elements, where you have to combine the information from several glTF elements, for example, meshes and mesh primitives, where you have to establish the connection between the mesh definition and the buffers, buffer views, and accessors that contain the actual geometry data. Then the next step would be the rendering, that consists of techniques and materials and programs and shaders, depending on which approach you are using for rendering. When you intend to write a GL-based renderer, then you will probably use the technique extension. When you are writing a Vulkan-based renderer, for example, then you will directly use the material definition that contains the parameters for a physical-based material in glTF 2.0. And the most sophisticated example or concept is probably skinning, because it combines all the elements of a glTF asset. It defines meshes that are deformed based on the skeleton hierarchy. This consists of nodes. Usually these skeletons will be animated, and finally the resulting geometry has to be passed to the renderer in a form that, so the renderer has to be aware of the fact that there's vertex skinning going on, so that you need a dedicated renderer that can interpret the input information that is provided by the techniques in this case, that for example the weights and joint information for the vertices, and that defines the information how to transform the mesh. That usually happens in the vertex shader. So the skins really are the most sophisticated concepts appearing here. To get started, I recommend to have a look at the existing loaders and viewers. There's already a long list with different languages: JavaScript, C++, C#, Go, Rust, Haxe, and Java. And there are already different libraries that offer the basic functionality of loading a glTF asset, so that you can directly use these libraries when you just want to render the assets, for example. when you want to contribute in any form to glTF or the glTF ecosystem, for example, when you want to write loaders, exporters, or viewers, then you can notify us, and the loaders or your work will be listed at the main landing page on the GitHub repository. You can also contribute sample models that will be added to the official sample models repository so that others can use your sample models for testing certain features. You can also write tutorials that will then be published in the Khronos GitHub repository as well. And when you're already using glTF, then you can drop us a note and show us what you have done with glTF already. So this concludes my presentation, and can you see a set of final links here. The general landing page when you want to download the specification or tutorials. You can sign up for the Khronos newsletter to always be informed and up to date with the latest developments. You can have a look at the Khronos members page and learn about the details of becoming a Khronos member. When you have questions about the slides, then you can just write to the mail address that is given there. And finally, I would like to thank all glTF contributors, and thank you for your attention. And now Neil Trevitt and Patrick Cozy will join to answer your questions.
Thank you very much, Marco. That's really great. That's a great presentation. We do have some questions here. Neil and Patrick, are you guys able to unmute yourselves, or let's see if I can unmute you. There we go. All right, so go ahead and take it away, guys.
Okay, well, perhaps I can start. There's a couple questions here on the ecosystem and the timelines for 2.0 and when people should switch to 2.0 as opposed to glTF 1.0. So I've actually typed in some answers, but just to go through it verbally too. So the plan is to have a final review version of glTF 2.0 at Game Development Conference. That's the GDC coming up in San Francisco in a couple of weeks. And the idea is to have a complete final specification. And as always, it's being developed in the open on Khronos GitHub, so you can watch it come into being in real time. But at GDC, we'll have a finalized version where we're expecting and requesting last round of feedback from the developer community. And then the plan is for the working group to finalize 2.0 just as quickly as we can once we have received and integrated that feedback. And there's a related question there too. If you're writing parsers and using glTF, should you support 1.0 or 2.0? In general, we think that 2.0 adds a couple of good things to the ecosystem, as well as adding additional functionality like PBR, the physically based rendering. It does simplify processing, actually, in a number of places, particularly around animation. And so in many ways, it's a cleanup. It's actually easier to process 2.0 in some ways. So we're encouraging the ecosystem to move towards 2.0 as quickly as we can. It's not a lot of work to go to 2.0, so we're hoping that we can converge on 2.0 as an industry pretty fast.
All right. Patrick, are you with us? Are you able to take on the GLB question and the Vulkan question?
Sure. So for GLB, so that's currently the binary glTF extension for glTF 1.0. We are actually building binary glTF into the core 2.0 spec. So basically what that means is there's a buffer view for images that allow you to pull images out of the binary blob as opposed to a separate image file. So .glb will be pretty much core in glTF 2.0. I'm still trying to find the Vulkan question.
So the Vulkan question is any advice for loading glTF files into Vulkan, given differences in GLSL?
Yeah, so with glTF 2.0, PBR will be core, so you won't necessarily have to deal with the GLSL. You can generate shaders directly from PBR. I have not written a Vulkan renderer myself, but there are a handful that are out in open source. So we could, if we can post any notes with the webinar here, we could send those out. They're also in the README and the main glTF GitHub repo.
It may be worth mentioning that many of the changes that have been done for glTF 2.0 have been aiming at a broader or simpler support for Vulkan. So many of the changes have been inspired by people who wrote Vulkan-based renderers. So it might be a little bit simpler for implementers to adapt to glTF 2.0 in Vulkan.
An early question that we got was about the nodes. Does a node index start with 1?
It's not supposed to, no?
Now, so in glTF 1.0, the top-level objects were top-level properties were objects, so they all had a unique name. In 2.0, there'll be arrays, so that because they're faster and easier to access, and those will be zero-based arrays.
All right, another question was, how would blend shapes be represented for animation? Are matrices the only form of animation supported? Any answers to that one?
Marco, do you know offhand?
I'm admittedly no. I'm not entirely sure what is referred to with blend shapes. I think that there have been some considerations. I think Alexei did some work there, but I'm not sure about the current state, admittedly.
Yeah, it may be best to open an issue on the GitHub repo so we can have the right person answer this. I mean, briefly, the animation support in glTF is keyframe animation, for translation, rotation, and scale. And then in 2.0, they're putting in morph targets for things like facial animation.
Actually, the second part of the question, are matrices the only form of animation supported? This refers to the matrices that are built from the translation, rotation, and scale properties of a node. I don't think that there is currently a support for more than that, but again, I think that Alexei did some work in this regard. Best thing would probably be to discuss this in a GitHub issue. Yeah.
So there's been an update to the question here saying it's morphing like heartbeat cycles. So yeah, so this is part of glTF 2.0 with the morph targets, and there's a discussion right now. It's pretty close to converging on the spec, and that all is public in the GitHub repo.
Excellent, thanks, guys. Another question, is it recommended to say custom properties and data values or other specific things for games and apps directly to the glTF file?
Yes, you can. So you can add an extras object to any of the other objects in glTF, and then inside that object you can add any properties that you want that are application specific. The other thing that you can do is you can combine glTF with your own format. So you might have like a binary blob that contains glTF, and then it contains metadata, maybe for some of the objects in it, or maybe it contains environment data. You can kind of do either approach.
It says, is there room in the format for custom properties?
Yeah, that's kind of the same question. So custom properties can be added to any extras property, and you can put whatever type of data you want in there, whether it's array, other objects, intrinsic properties, and so
on. Okay. Does glTF support baked animations?
So I might not be completely familiar with the terminology, but I think this is similar to the morph targets, where you could have multiple meshes and then blend between them. And if I'm wrong, please comment here, and we'll try to get your question answered.
Why do we not use accessors as buffer view too?
For me, this question is not entirely clear, but these are different concepts. The buffer view is only a part of a buffer, and the accessor contains a reference to the buffer view and additional information about the structure of the data that is contained in this buffer view. I'm not sure whether this answers the question. Otherwise, it might be rephrased a little bit.
All right, we have one more question. It says, are there any examples of a 3D line primitive, or is this kind of covered with a skeleton?
The mesh itself is basically a very simple description of the geometry data, and it also contains information about the rendering mode. So, for example, you can have a mesh with an accessor for positions, vertex positions, and the information that these should only be 3D lines instead of triangles is contained in the rendering mode of the mesh primitive. I think there are currently no examples in the official repository. I have seen an example in, I think, the 3JS repository. Maybe we can add this example or a similar one to the official repository as well, to have an example for 3D line primitives. It's fairly unrelated to skeletons, apart from that.
All right, well, we have no more questions. Marco or Neil or Patrick, do you have anything you'd like to add?
Well, I'd like to add we are going to be at GDC, so if anyone on the call is going to be at the Game Developer Conference, come chat with us. We have session on the Tuesday on the GDC program. We also have a meetup on the Thursday evening. All the details are on the Khronos website. It'll be great to see some of you there. And perhaps just to chat briefly about some of the tentative things that we're looking at beyond 2.0. Some of you might have seen the Draco mesh compression, which is a pretty awesome technology coming out of some teams at Google. We are talking to those folks because glTF is well architected to enable binary payloads to be compressed with various techniques, and it seems like there is potentially a good synergy between glTF and the Draco technology. So that's a discussion that's ongoing. We're really interested to kind of get your feedback. The GitHub repository is the best place to leave feedback on what you'd like to see in future versions of glTF. So things like compression and streaming for large payloads is certainly something that we're looking at, but we're interested to hear what's key for your workflow too.
Not to mention, you can get an awesome glTF T-shirt at that session.
It all comes down to the T-shirts.
Right. Yep. That's right. All right. Well, thank you very much for joining us. As I said at the top of this presentation, the video of it as well as a PDF of this presentation will be available on the Khronos website, and you will all receive an email shortly with the URL where you can get that. Thanks very much. Bye-bye now.